to the top of your screen right now? Oh, there you go.
Ah, gosh. Okay, so do I have to explain this one more time? Okay, let's go back. Let's go back. Reaction rating, no problem. Okay, you need 2 moles of the Grignard reagent, okay, to react with the benzoin. If I give you 1 mole of benzoin, I need 2 moles of this Grignard reagent. 1 will go to this hydroxy group, take away that hydrogen. At the same time, you're generating methane gas. The other molecule will come to the carbonyl carbon right here and attack to produce alkoxide. Okay, for each molecule of benzoin, you are creating 2 sites. 2 sites. Before acidifying it, you're creating 2 alkoxide, okay? One from the original hydroxy, the other from the carbonyl group. You're generating 2 alkoxide right here. So this is a very important stoichiometry number of moles to be considered, okay? Okay, alkoxide within this molecule, before it is acidified, there are 2 sites. 2 sites. So I want you to go back to my Grignard reagent writing, okay? You know, from benzoin, you already know I need 2 moles of Grignard reagent. And so from this generation of Grignard reagent, you know this is actually seeing this carbon keep this electron pair tighter compared to the magnesium. And for this reason, it is a strong base. You also want to consider this as being a potential base for the reaction of the hydrogen on the sulfuric acid. Okay, this is quite important because a lot of you actually forgot. Okay, and so how does Grignard reaction go? You see this, okay, attack this carbonyl group in addition to the hydroxy group that will get attacked on the benzoin, okay? So everybody know that, okay? The problem is when it comes down to the stoichiometry, okay, people forget that the hydrogen from sulfuric acid will have to go to 2 different places. One will go to convert alkoxide to alcohol. The end product is alcohol, okay? And I want all of you to just open the page on your reagent table. Your moles of a benzoin is this much, okay? And because you are creating 2 sites on the benzoin, both alcohol group in benzoin, also the carbonyl group, 2 sites of alkoxide right there. And for this reason, you need 0.00472. This is actually double the amount of a benzoin. Okay, you need this much moles of hydrogen to protonate that product, to protonate that alkoxide, okay? Okay, so this is one important requirement, okay, for sulfuric acid to react. The other part of the reaction will take place when I said this Grignard reagent being the base and it needs to be reacted, okay? Why is this a base? Please go back to the structure one more time. Is this a base? Yes, because the electron pair is more to the carbon side. So it has the potential to function as a base. And actually Grignard reagent is a strong base, okay? I did show this reaction in the lecture a couple of weeks ago. Grignard reagent definitely will take away the carboxylic group, okay? And in this case, we don't have carboxylic acid. What we have is the sulfuric acid, right? Also, yeah, also that reaction produced the methane gas, okay? And so don't forget, the remaining part of the Grignard reagent will need the protonation. Sorry, will need the reaction with the sulfuric acid. So what is the product, everybody? When you react Grignard reagent with sulfuric acid, what is the product again? Lee-Lin?
Methane gas.
Yeah, it is methane gas. And what's left? Okay, you will have magnesium +2, okay, coupled with SO4, right? That's one possibility. Or you can have magnesium and iodide, and then that is plus charge. And then people write, hey, maybe I have 2 of this magnesium bromide with +1 charge, and then I need 2 units of that to counter the SO4, the sulfate -2 charge. That is also acceptable, okay? I don't mind if you write the reaction that way, okay? And the main thing is your sulfuric acid is going to 2 different places. One is to react with the alkoxide group, okay, created during the benzoin. Okay, remember the benzoin reaction writing, okay? So you need 2 hydrogen plus right there, and the other hydrogen plus will go to react with the remaining Grignard reagent. In this reaction, you also produce the methane gas, okay? Most people just completely forgot about this. And I want to go through some number with you, okay? Moles of benzoin is this much. And because on this benzoin, and after the hydrogen deprotonation, after the carbonyl group being attacked, you have 2 alkoxide generated at the same time within the same benzoin structure intermediate, okay? And that one has 2 hydrogen plus, so don't forget this is the number of hydrogen that will have to be used later, okay? In addition to that, let's do some calculation about the Grignard reagent remaining amount, okay? Because based on magnesium amount, you have 0.012 mole of Grignard reagent formation. This is actually coming from your reagent table. Everybody knows that, okay? But after the Grignard reagent being used in the reaction here, remember one goes here, the other one goes to the carbonyl group, okay? After that, there will be some remaining amount, okay? So how much is the remaining amount for the Grignard reagent? Because I know, okay, this amount of moles of the Grignard reagent will be consumed in the reaction with benzoin. So I know there will be so much left over, Grignard left unreacted, okay? And this all needs to be protonated. Do you all agree with me? Okay, so during this protonation, you will write the CH4 and some sulfate salt as a final product, okay? All right, so in order to react with the alkoxide, okay, you need this amount of moles of hydrogen plus, and also the remaining amount of the Grignard reagent, you need 1-to-1 ratio, okay? So when you add this 2 number, I said the number from process 1 and number from process 2, the combined required amount of hydrogen plus that will be used in the reaction is this much, okay? And so when you calculate the required amount compared to the amount of moles hydrogen plus provided from the sulfuric acid, you know you do have enough, okay? It is because, okay, this, remember the moles of proton calculation I asked all of you to do, okay? And I hope you all understand, okay? A lot of you actually just miss out this part of the reaction on the remaining region of Grignard. And this is why you lose 1 point, okay? For the whole entire class, there's only one student got this right, okay? So far, are you getting this mole business stoichiometry straightened out?
Yeah, I'm getting a better understanding of it now that we're going over it.
Yeah, okay, all right. So that will be the, you know, everybody made that mistake except one student, okay? And the second part of the worksheet, let me see, what else is there? Okay, Grignard worksheet right here. Okay, most people do well, okay, with the IR, yeah, no question about it. Now, starting from question 5, 6, and 7, you will need to draw the intermediate. Intermediate is not a good word. I should say transition state. You want to draw the structure of the transition state in order to predict the major diastereomer product. And each is 6 points. It is actually putting you on the test, whether you understand this CHEM model versus the Falcon-on model versus the chelation model, okay? And I just want to point out at the end, question number 8, determine which model is more effective predicting the product. I can tell you the answer is all 3 leads to the same answer, and the product is 2, 8, right? You all remember this. And let me go back to the model, okay? All right, so the CHEM model first. Most people got this part right, okay? All you have to do when you do the CHEM model is just to line up the carbonyl group, okay, and the other side you have a phenyl group, everybody knows that. And CHEM model just says, I will just attack this carbonyl group carbon from the side that is least hindered. So when you rotate a single bond between the carbon and then the chiral center carbon, you will be able to find this is the right conformation or Newman projection, and you attack this carbonyl carbon from the least hinder. Usually people just put the hydrogen, okay? If it's, you know, all you have to compare it is between this 1, 2, 3, between these 3 substituents on the chiral center, you just need to rotate it and then put the hydrogen at the side, and then you add, you can introduce your Grignard reagent, okay, from the hydrogen side, because it has 2 directions, right? One is this way, the other way is coming from the left, because you know this is a planar, trigonal planar geometry. Am I right? Okay. And then, so after that, you would generate this product. And most people got this part right, okay? People do have problem with the second model, okay? Now, Lee-Lin, I want you to pay attention now, because I think there is a little bit small error in your transition state writing, okay? Okay, remember when you do the Falcon-on, okay, you line up your carbonyl group, and then the other group, whatever that is from the question, okay? And then you want to put the most bulky group 90 degrees relative to the carbonyl group, okay? That is the requirement, okay? 90 degrees. So you have 2 directions. One is putting the phenyl group, this is coming from the chiral center. You can put that 90 degrees on the left-hand side of this trigonal plane. The other choice is to put, okay, now you have the same, okay, the same trigonal plane right here. Okay, you can also put the phenyl group 90 degrees to the carbonyl group. Either way, okay, Falcon-on model just asks you to do that as step number 1. Okay, 90 degrees, bulky group to the carbonyl group. Then what's next? Now, this is what people make mistake with. Right here, you just need to watch out. When you introduce the Grignard reagent, you want to do it 107 degrees relative to what? relative to the carbonyl group. Are you all with me?
Yeah.
Okay, so you have 4 directions, 4 pathways to approach this carbonyl group, right? You can do it this way, where my arrow is, and I can do it the other way. I can come this way too, and it is still 107 degrees, right? Do you see where I'm pointing at? Okay, so there is pathway here, pathway from this side, or you can write the Falcon on, okay? When you put your phenyl group, the most bulky group from the chiral center, 90 degrees also, but this time it is at the other side. So your Grignard region can come also 107 degrees this way or this way. Am I right? This
Yes.
is where I'm pointing at. Okay, so I ask everybody, 1, 2, 3, 4. Which way is least hindered? Of course, this top one is the best, right? Because, yes, because this is showing you, yes, I am getting the least hindered direction of attack. Am I right? I don't want this direction of attack because oxygen is much bigger compared to hydrogen. Don't forget, 107 degrees angle is what's required in the step 2. You see that? Do you see where I'm showing here, right here? Carbonyl group and then the Grignard region, okay? They are 107 degrees from each other. Okay, it makes sense, and I explained once. It doesn't want to come the other way because if you, okay, follow my hand right here. If I come this way to attack the carbonyl group, you know this is electron-rich area with carbonyl double bond, and your Grignard reagent is electron-rich. They are not gonna like each other. So 107 is much better. Am I right? Okay. Yes. And 107 this way is not preferred because I have bulky phenyl group. Okay. All right. The same explanation goes to the other direction. You are not gonna like this, okay? Because the oxygen is much bigger than having only 1 hydrogen here. Am I right? So this is the right attack. And you, of course, you're not gonna do this, okay? No one will do this, okay? So there are only 2 scenarios, you know, for your level to pick one, okay? Of course, you will pick the one on the top, which is the product in 2A, right? Okay, so do you understand now with Falcon on, don't forget, bulky group from the chiral center carbon, okay, will be placed 90 degrees vertical to the carbonyl group. Then you decide, okay, the attack from 107 degrees. Okay, this is very similar to the tetrahedral bond angle. You want 107, if you say 109, is that okay? Yes, 109 is also okay because you will draw it the same way. Okay, so pathway 1, 2, and then 3, 4, it is this one that is considered correct Falcon on. Are you all with me?
Yes.
Okay, all right. Now, Lee-Lin, you just made a small boo-boo here.
Yeah, I know. I had the placement of the alkoxide and the hydrogen switched.
Ah, okay.
So that's what gave me the that's why on my thing I said I gave the RR isomer, which isn't
I got it. Yeah, I remember you did it. Okay, I can tell you a lot of people don't even know when we want the student to answer the question based on the chiral center with the R direction. And a lot of people just wrote the other way, okay? No, you have this 1, 2, 3, okay, hydrogen phenyl, and then this oxide. Come on, you know, definitely oxide is much bigger than the carbon, which is the first element. So it has to be 1, 2, 3 this way, right? On the chiral center. Am I right?
Yes.
Okay, a lot of people just did it the opposite way. Of course, you will lose credit, okay? All right, and can I move on now to the chiral, no, wait a minute.
For the chelation?
Yeah, the chelate one, okay? I did it with my own hand drawing, okay? And I want to do it this way, it's actually easier because you know you can form chelating. Once you put two oxygen together, the carbonyl oxygen, and then if you have oxygen on the chiral center, you know this two oxygen can actually help chelating, right? With magnesium. So what does it mean when you write the transition state? How do I enlarge it now? Hold on. Is it better?
Yes.
Okay, your nucleophile, still the Grignard reagent. Okay, this is your, your reactant. Okay, after deprotonation, okay, you have this geometry. All right, and then your nucleophile, which is the Grignard reagent, will be coming to, okay, again, 107 degrees. Okay, you will still do the bulky group 90 degrees. Okay, the same way as you did on the Falcon on. Okay, the only difference is now you chelate it. You chelate the two oxygen together. That will put the phenyl group and then hydrogen in the place according to distribute the three substituents to share this 360 degrees space, and then you'll find this one hydrogen right here. Okay, so this is sequence 1, 2, 3. Okay, from smallest to large. The the clockwise direction, and then you can see my nucleophile actually can attack this 107 degrees easiest from this direction, and this is how you can generate the product the same way as before, and the prediction is 2A. Am I right? And I call this R and R because I view it from this angle, okay? And so, of course, if you assign it with the according to the the rule you learned in the past, it will be R and S, okay? And I just want to view from this angle and to tell you this is actually clockwise and clockwise, okay? You see this clockwise and clockwise. Hydrogen, phenyl, and then oxygen, 1, 2, 3. After the nucleophilic attack, it is still 1, 2, 3. If you view from this same direction where you're outside of the computer screen, you from this angle, you're viewing it, is that you get this two clockwise, okay? You both clockwise arrangement of the substituents, okay? So after protonation, you get that product. And I hope all of you understand now this three models actually has a little bit difference in the procedure when you follow the rule, structure the substituents, okay? And the same rule is that you will approach the carbonyl group from the least hindered place. With chelation here, you will be able to put your substituents on the chiral center actually in a much easier way. Am I right? This is the only way to put them. And it's actually the easiest. I would say this is the easiest. However, you still have to know that three models leads to the same answer though, okay? And so I hope you get it now. Common mistake is actually on the Falcon on, not on this one. People all know about this. I think the Falcon on model is the one that people cannot really see, having this phenyl group 90 degrees. Okay, oh, wait a minute, this is the cream model. Okay, it is the Falcon on, whether you have the right direction or at all when you put the phenyl group. Okay, that 107 degrees is the key, okay?
Sounds good.
Is everybody okay now? Okay, then any question here at all? I want to know, do you want me to clarify anything?
I think it's pretty straightforward.
All right, yeah, actually this chapter, yeah, it's not too bad. If you're comfortable with the molecule drawing, Okay, you have to do it yourself. Use your own pencil. You don't just follow the slides and then listen. You have to do it yourself, okay? Then you, once you go through one example, you see all of the examples actually. It's easy now, okay? All right, I think I'll just stop right here unless you have more questions. Hello?
On the CRAMS chelation, so I asked Dr. Lopez during class,
Mm-hmm.
when it's going through the transition of the actual, it's making that the actual so-called bond with the Grignard reagent. I asked, is it still possible to chelate even though the magnesium iodide's already attached to the actual oxygen right there? So like on my example of what I wrote for the CRAMS chelation is on the O negative, I have the magnesium iodide connected to it as it chelates, and he told me yes, it can just that's still correct for it to chelate that way. But I see in your drawing it, you don't have the magnesium iodide connected to that oxygen.
You mean here?
Right here
Yeah.
where the O negative charge is, if you right where that O negative charge is, instead of having just O negative, I have the O magnesium iodide. And what Dr. Lopez told me was it can still chelate even if it has the magnesium iodide attached because of the lone pairs on the oxygen. But I was just curious because I don't see the magnesium iodide in your diagram. Like connected to the oxygen?
Right here?
No, the first mole that when it reacts with the alcohol.
Okay.
So if you like, can I share my screen real quick?
Okay.
If you can allow me to share my screen.
Yes, yes. How do I do it?
I have no idea. I think you have to somewhere in your options.
Okay, ho. Are you talking about this file or the crane model file?
No, CRAMS chelation, the one you were just showing.
Okay, yeah. Are you saying, do I have to use iodide here?
No. So how I drew my transition state of how the second mole of the Grignard reagent binds to the two oxygens. On my oxygen with the negative charge, instead of oxygen negative charge, it's the oxygen with the magnesium iodide attached to it already. And then the second mole is showing the chelation.
Okay, Dylan, I don't know whether I understood your question correctly, okay? With this magnesium, okay, why is it capable of chelating? It is because it has empty S and the P orbital. Do you agree?
No, I understand that. I'm just showing the way you're showing it is you don't, like, if you go back to the CRAMS or the Falcon On, in our transition state, we show that the magnesium iodide is already attached to the oxygen right there.
I see.
So what I'm saying is in my CRAMS chelation model of what I wrote, I already showed the magnesium iodide attached, and then the second mole is showing the chelation because I asked in class Dr. Lopez, and he told me that that's correct, that it can still do that because of the lone pairs on the oxygen.
Exactly, I agree.
So are we going to get marked off if we already
No,
showed?
No. I don't mark off that way. No.
Okay.
No, not at all. Because I can tell you, I mean, even at during this stage, you know, there are a lot of scholars trying to really find out what the real structure is. I don't think there is a policeman here saying that you can't put a chelating here, or after you're talking about this one, right? This oxygen, it was actually magnesium. The first Grignard reagent after deprotonation, that alkoxide is already showing a strong favoritism to this ionic species. There is a strong attraction. It is a natural attraction. It is just when the bond rotate, okay, the molecule will find a comfortable position this way too, because it does lower the energy of the transition state. Understand?
Yeah.
Because chelating is actually it can help stabilize that species, that molecule in the transition state. And this is what these scientists realized the chelating agent, or oftentimes this is the Grignard reagent or the Lewis acid, all have this great power doing this wonderful job, stabilizing it. Understand?
Yes.
Okay, so you learned from Lewis acid, remember? Yeah, that magnesium +2, yes, it's capable of doing this too, okay? So far, so good?
Yeah.
All right. So I think we can no, I can stop now. And the reason I want to stop is just because I don't want to make this recording too long. And when I take questions, okay, should I just stop share? Oh no, I shouldn't do this. Can I just pause recording?
Yeah. So go back to where you go for recording.